Welcome to the Dynamic Learning Hub of XLR at Andheri East. Conveniently located at just a 5-minute walk from Andheri Metro. In our journey of over a decade, we have proudly trained over 2 lakh students. We've also been recognized by Deloitte, Silicon India, and other accredited. Experience learning like never before in our spacious and comfortable classrooms. With high-definition projectors and state-of-the-art acoustics in place, we ensure effective learning even to the farthest point in the room. The hybrid mode is a game changer as you can enjoy the benefits of a light classroom from the comfort of your home. Even if you happen to miss any classroom session, you can still attend the same session with the same trainer at the same time at your convenience in progress. Wanna get started? Join us for a demo or career chat over a cup of coffee at our Andheri branch. XLR. We don't just train, we build careers.
Yes, so the collaboration with XLR was an excellent one. We conducted a Power BI workshop with Advanced Excel over a span of 3 days. The workshop was almost 12 hours long in total. Mr. Karthik, who understand deeply should
Karthik was an where he explained in very detailed manner on how to give great insights using very complex data sets.
So it was a machine learning workshop. We learned a lot from the course and it was a great experience attending the workshop.
The trainer was very helpful and it was
experience. So
Good evening all. I hope you all doing well.
Hello.
Good evening, sir.
Yes. May I start?
Yeah, you can start, sir.
Sure. Good evening to all of you. I hope you are having a great day, guys. So yesterday we have started with the battery pack technology, which is very new to you guys. And we are continuing those parts today also. So basically yesterday we covered the basic chemistries and what are the pros and cons of two chemistries, especially NMC and LFP. So I hope you got some points on NMC, some points on LFPs. So in future, whenever actually you are going to be a part of this EV market or EV domain, so obviously means you will be cleared, right? Means what is NMC, what is LFP, what is the nominal voltage, what is the full charge voltage, what is the cutoff voltage for specific chemistries, means why actually what are the advantages of lithium ion irrespective to means whatever the lead acid batteries we are using. So I think that is cleared. And today actually we will cover the cell form factor, which I actually skipped yesterday. But today we will start with okay. Yes, I think my screen is visible to you all.
Yes, sir, it is visible.
Yeah. So basically lithium ion cell form factor means what is the shape of the lithium ion. So mostly I think you guys have seen cylindrical cell mostly because whatever the cells actually we are using in case of remote controls, in case of other appliances, I think you have seen cylindrical cells because it is a very common structure. But the other two types of structure, I think you may not have seen because this type of structures are only used for in EV domain only. EV, and nowadays, obviously, I told you that there is a new sector that is battery energy storage system, which is basically used for solar generating stations and obviously whatever we are supposed to replace the generator set. So on that case, actually, we are deploying battery energy storage system. So most of the, we can say more than 90 means 95% BESS battery energy storage system are made up with prismatic lithium cell. The first one that is named as prismatic. So this form factor, whenever suppose you are means you are having this type of cells, means this type of structure, so you can easily named it as a prismatic structure. And after that, the second one, that is the pouch lithium cell. So I think the second one also you are familiar. So in which applications we are using this type of pouch structure? Just a quick answer round, right? I'm giving you just 60 seconds. Please tell me, guys, means the second one, that is a pouch structure, where means what is the, we can say, the major application of this type of cells. And it is very common to all. Come on, guys. This would be an interactive session. You have to answer, means whatever it means in your mind, just say it. Cylindrical cells already you know. Prismatic I told just. And pouch is a very common structure. So basically pouch is widely used in mobile phones. So you have seen mobile phones battery. So basically from decades actually when we are having NIMH, that time also we were using this type of pouch form factors. Nowadays also we are using pouch form factors. So there is an advantage and disadvantage of this type of pouch means structure. So we will see later. But these are the major three structures actually we are using in case of EVs, right? Now, this is a cylindrical structure. How actually a cylindrical cells manufactured? So basically, in case of cylindrical structures, actually we are using a foil type rolls. We can say, see, we know the components, right? What are the components actually we are using? So there are anode, there are cathode, there are electrolyte, and obviously there is a separator. So every component actually made up with means foil type. Actually, we used foil type separator, foil type aluminum sheet, right? Aluminum sheet as a positive, we can say as a cathode electrode, and in case of negative electrode, we use copper. So obviously copper foil we are using, and that are sandwiched and roll up and packed in a cylinder. As from the diagram also you can understand that how actually it is rolling up inside the cylindrical can, right? So what is the advantage and disadvantage? uh, See, it is absolutely depends on you which type of cells actually you want to choose, right? It obviously, see, suppose in EV you have to build a battery pack supposed to be 300 volt, 100 ampere hour. And obviously there should be a multiple series parallel operation. So obviously you may use prismatic, you may use pouch, you may use cylindrical. So which type of cells are best suited for EV? So that is why actually we need to know about the advantage and disadvantage, right? In every structure. So in case of cylindrical cell, actually, we are having a high mechanical stability. So that is the first point. So that is why actually, because of this mechanical stability, Tesla is also using this type of cylindrical structure cells. And the second point, that is also a advantage, and that is why also Tesla using this type of cylindrical cells. That is a efficient thermal management. So obviously, actually in the thermal management session, actually we will get how actually we can say extracting the heat from the cell surfaces. So from cylindrical cell surfaces, it is very easy to extract the heat. So that is why obviously if means we can apply the external thermal management also, but in this structure, actually the heat dissipation is far better than other structure as compared to pouch cell and the prismatic cell. Now, it is widely available. See, in a product, suppose we are manufacturing a cells, there are means two main component. One is first, that is a R&D cost. After that, there is a manufacturing cost. So in case of cylindrical cell manufacturing, the cost means it is easily we can do mass production, right? And automation available. And as you know, from a decades ago, actually we were using this type of cells, cylindrical cells, right? So that is why actually mass production can be possible with a very low manufacturing cost and the standardization and availability. So I have you can see that here I have written 18650 21700 4680. What does it mean actually? Whenever actually you are searching for a lithium ion cells, suppose you are searching in Google, you need a lithium ion cells. So obviously there is a cylindrical cells you are searching for, but in cylindrical as well, there are multiple types of cylindrical structures. So what does it mean 18650? So yesterday I have shared a data sheet. So let me open those data sheet again. From that it will be cleared. So guys, you can see that is written as 32140, right? 32140. Cell type is 32140. So the first two digit 32 is actually your diameter. One second. So you can see that is 33.2 plus minus 0.2. So mostly it is 32 plus minus 1. So whatever the cell diameter actually we are using, so we are writing it on the first two note. See, this is the designation 32140. So 32 you can see they written separately and 140 they have written separately. So obviously 32 means the diameter and 140 is the length. So this means this type of cylindrical cells are manufactured from past 3 to 4 years. This type of means it is a very big cylindrical cells. Whatever the cylindrical cells we are seeing in the market or in home appliances, especially in home appliances, we have seen this type of cylindrical cells. But this form factor 32140 is very new. So let me open the PPT again. So I have mentioned here 18650. So please don't be confused. 18650 doesn't mean that means 650 is a length, right? 650 mm length is huge. So basically, whenever actually this type of standardization started a year back, means 10 to 15 years back actually. So 18 is your diameter and 65 is your length, and all the dimensions are in millimeter. Please be noted, all the dimensions are in millimeter. So 18650 means 18 will be your diameter and 65 will be your length. Same as 21700. So these standardizations also available from past 10 to 15 years. So that means 21 is your length and 21 is your diameter and 70 is your length. So nowadays also we are using 32650. 32650 in LFP. In LFP chemistry, actually, we are having 32650. And this 18650 is very common in NMC chemistry. 18650, 21700. So these two type of cells structure actually widely available in NMC chemistry. For LFP chemistry, there is 32650 or 32700. You can easily search it on Google. Just note it down, these standard factors, 18650, 21700. So you just write it on Google, this type of cells, you will get a cylindrical type of cells. But in case of 4680, this 4680 standards actually set by Tesla. Only one manufacturer, that is Tesla, are producing this 4680 cell. So 4680 is nothing but 46 diameter and 80 length. So they have set their own standard, right? They doesn't follow that 46800, right? They have set it their own standard 4680. So 46 dia and 80 length. So that are the NCA chemistry actually they are using. And in every means in their vehicle they use their own cells, right? And these are the form factor of that cylindrical cells. Okay, what are the disadvantage? So obviously every type of structure having their advantage as well as their disadvantage. Low energy density. Now, don't be confused on low energy density means there is a two type of chemistry. One is LFP, one is NMC. Suppose you are using a NMC cell, right? Just take one chemistry. Suppose you are using a NMC, right? So in NMC, there are three type of structure. So in this cylindrical type of structure, there is a low energy density, right? Because more space is wasted due to the cylindrical shape. Because due to packing, actually, there are more space actually wasted. And you can see that mostly these type of cylindrical cells actually having a very low capacity, 2 ampere hour, 3 ampere hour, 5 ampere hour. So these are the rating. And obviously, these type of cells having higher weight. If we can say, obviously, low energy density means higher weight. It is actually proportional. If you are using high energy density cells, obviously the weight will be lower. So that is a vice versa. And there is obviously limited customizations available. So whenever suppose in the battery pack design session, basically we will discuss, means I will cover this today itself. So you can see that you will see that whenever actually we are designing a battery pack, a more number of cylindrical type of cells we have to use because the rating is very low. 2 ampere hour, 3 ampere hour, 5 ampere hour, these small cells we have to use. So whenever we are designing a big EV battery, so on that case, we have to use nearly 1000 number of cells. So it is very difficult to place those cells properly. And obviously, there is some rules and regulations are also there whenever you are designing a battery pack. So this means you are seeing on the cell level now. So whenever we will be in the battery pack level, obviously there would be a pros and cons of this type of structure. And obviously it would be more complex assembly because you have to do more series, more parallel, right? To basically design those high voltage, high ampere hour battery packs. So that is an advantage and disadvantage. Now let's come to the prismatic structure. So mainly in case of prismatic structure, we are actually using sheets. It may be 1 mm, it may be 1.5 mm sheet type structure actually we are using. So there are also a same thing you can see from the diagram itself. You can easily understand that there is an active material, there is a current collector, there is a again there is a active material, means I'm talking about positive negative electrodes, and as well as the separator. So this type of arrangement actually we are using in prismatic structure. So there is also a advantage. So this type of structure having a higher energy density than cylindrical cells. And mostly I have shown you two types of cell yesterday. One is cylindrical type and another one is prismatic type. You can observe, I don't know you have observed or not. So in case of cylindrical cell, that was on 15 ampere hour. That is very less, 15 ampere hour. But whenever you have seen that prismatic structure, that was 50 ampere hour. So nowadays, 300 ampere hour cells also manufactured. Means 3.2 volt, I am talking about in LFP chemistry. 3.2 volt nominal, that is average voltage. And 300 ampere hour cells also we can produce nowadays. But in cylindrical means in those shape, cylindrical shape actually, it can't be possible. So that is why means we can say this is a flexible design. Whenever actually we are designing by prismatic cells, we can easily place those cells according to our structures, right? EV structures. So mostly if you see Tata, not Tata, if you see Mahindra, if you see MG, Kia, so this type of means four-wheeler players are actually using prismatic structure, but Tata actually using cylindrical structure, right? Tata is using cylindrical structure. So that is why actually Tata batteries are so much heavy, because cylindrical structure already having a low energy density. See, Tata use LFP chemistry, right? So LFP chemistry itself having a lower energy density. And in this lower energy density chemistry, they also use cylindrical structure. So obviously for mechanical stability and thermal management, these two are the main factors. See, already we know guys that for Tata safety matters, right? Safety is the best thing that they can give. So obviously they always means try to design a safer battery pack. Those battery pack would be more mechanically stable, as well as there should be a very good thermal management, right? Because obviously we know that what is the Indian weather, right? In summer there is a 40-45 degree temperature goes up, right? So on that case thermal management will be required. So that is why, yes, maybe the weight is increasing, but obviously the safety is also increasing. So that is why Tata choose cylindrical cells only. Now there is some other advantage also, simpler battery pack design in case of prismatic structure. Obviously, see, every points are actually depending on your energy density and obviously the shape. So this is a rectangular type shape. So obviously it would be better to use this type of shapes whenever actually you want to design a very simpler battery pack. In case of e-rickshaw, you have seen three-wheeler e-rickshaws as well as e-autos. I think you have seen TVS launched their e-autos. I think Bajaj also have launched. Piaggio also have launched. So everybody used prismatic structure, and all the batteries are nearly same rating, 51 volt, 100 ampere hour. So I will show you that how actually e-rickshaw batteries means look like. Means I am sharing with you those type of pictures. Means CAD models types. What are the disadvantages of this type of prismatic structure? There is a high manufacturing cost. So whenever actually we are manufacturing a cylindrical structure, so there is a low manufacturing cost you have seen. But in case of prismatic, there is a higher manufacturing cost. And this type of prismatic structure having lower mechanical stability. See, mechanical stability obviously depends on your, means whatever the battery structure you are using, you should have a holder, cell holder, right? Whenever suppose you are designing a battery pack, you should have a cell holder. But in case of prismatic structure, if you are using cell holder as well, but that would not be more stable than a cylindrical structure. And also there is a point that is thermal management issue. Like heat dissipation is more challenging due to the large form factor. You already have seen that there is a huge form factor. Let me share uh, the prismatic data sheet as well. So this is basically the prismatic structure. Yes, that are the dimensions. You can see 142 mm is the width and 27 mm is the thickness. And you can see what is the weight, and height is 102 mm. So it is obviously a small, but actually this is a 50 ampere hour cells. Whenever actually we are using 100 ampere hour, 200 ampere hour cells, so they are quite big in structure. So obviously there is a lot of energy actually we are putting in one cell. So obviously heat dissipation should means otherwise we have to use a active thermal management, a good thermal management to extract the heat from the cell surfaces, or otherwise we have to use a lower ampere hour cells. So that is a drawback of a prismatic structure. Now there is one more structure, that is pouch structure. So this type of structure are widely used in mobile phone. In EV, we are not using pouch structure, very less. In two-wheeler, we are using. There are two, three manufacturer. There is a manufacturer named Sun Mobility. There is also a startup. So Sun Mobility actually having their means whatever we yesterday I told that the charging station means swappable station. So most of the e-rickshaws in NCR, I am talking about Delhi NCR. So they only use this type of swappable technology. So Sun Mobility also a key player in this swappable technology. So Sun Mobility are using basically prismatic type of structure, but this type of structure need a very high mechanical stability, because this type of means prismatic structure are not that much stable in we can say mechanical stability. I think you guys also have observed whenever our cell phone battery is also, it may be damaged due to circumstances. It may be overheating, it may be overcharging, over discharging, or maybe there is a live degradation. You may have seen the cells are swelling up, right? I think it is very common issue. I think you have seen in mobile phones. The battery is swelling up. So this is the main disadvantage of this type of pouch structure. You have seen the mechanical structure of mobile phone. Nowadays every mobile phone actually we are using that has a mechanical casing, right? Mechanical casing and very hard casing. We can't even open normally, right? But if you just take an example of a 10 years back mobile phone, right? So on that time we actually mostly used plastic cover, plastic back covers. So obviously plastic doesn't have a good thermal management. And that time also we are not using lithium ion battery technology. We used NIMH battery technology. So that doesn't need that much safety features, right? It in terms of thermal stability, in terms of mechanical stability, that doesn't need. But in case of lithium ion, you have to put these two factors. One is thermal and another one is mechanical stability. So whenever actually we are using this type of means lithium ion pouch structure, we have to give a good mechanical stability. So that is why we are actually pasting our back cover always. Whenever the new phone you have seen, so all the time actually the back cover is pasted, right? And if you see, obviously you know the heating, right? Whenever actually you are using cell phones from a for supposed to be 1 hour, 2 hour continuously, or supposed to be you are charging your mobile phones, you can just feel the heat, right? How much heat is dissipating. So as you are using a metal casing, the heat is easily extracted. But if you use plastic casing, then obviously the heat can't be extracted so easily, right? So that is why, but why actually we are using pouch structure? So it has a highest energy density. means it has a highest energy density, means higher than prismatic as well as cylindrical structure. So that is why it is adapted in mobile phones, cell phones I am talking about. So it has a higher energy density, very lightweight. Obviously, these are proportional, right? Higher energy density, that would obviously there should be a lightweight and highly customizable. Why highly customizable? Because when suppose in mobile phones also you have seen, right, there are different kind of different structured pouch cell. Actually we have seen there is a multiple types of, means in height, width, there are multiple things. I think you have seen there is a good heat dissipation. Why good this means heat dissipation is good? They are basically a thin like structure. The width is roughly around 10 to 12 mm. The width of these cells. I think you already familiar with mobile phone batteries. They are very thicker, thinner, right? That is roughly 10 to 12 mm. So that is why it is very easy to extract the heat from the cell surfaces. But in case of prismatic, the width is nearly 30 mm, right? And also the structure is means there is a mechanical casing actually we are using. In case of cylindrical, in case of prismatic. For both the cases, we use a mechanical structure to basically stable it, right? But in case of pouch structure, there is no metal casing, no metal casing we are using. But in case of prismatic and cylindrical, we use metal casing. So that is why actually we can directly extract the heat from the cell surfaces. But yes, obviously I told the disadvantages prior, that is a lower mechanical stability, swelling issues, and the lifespan is pretty much shorter. And there is a potential safety risk. As you have seen also, there is a fire cases in mobile phones, or means you have seen a many videos, I think. Now let's sum up with some comparison table. So how actually you will choose your form factor? So obviously, first of all, you have to choose a safer chemistry, right? Whenever you are choosing a cells for EV. So safer chemistry, obviously LFP is a safer chemistry. But in LFP also, you have to choose uh, the form factors. So depending on these features, suppose like the energy density. So you can see cylindrical having very less and pouch having highest. If we talking about weight, cylindrical are more heavy and pouch are the lighter one. If we talking about mechanical stability, cylindricals are very high, pouch is very low. If you're talking about safety, then cylindrical is very high, pouch is very low. So prismatic is the middle one, right? So that is why most of the manufacturer use prismatic cells. Mainly I have seen Kia battery, I have seen Mercedes battery packs, Kia, Mercedes, MG, Mahindra also. These 4 to 5 manufacturer I have seen batteries. So they use mainly prismatic structure. But some manufacturer like Tesla, they use cylindrical structure. I am talking about four-wheeler EVs, because in four-wheeler there is a huge number of series parallel structure actually we are using. In case of two-wheeler, it is not. In case of two-wheeler, everybody used cylindrical cells. Everybody, Ola, Ether, Hero, right? Okinawa, TVS, everybody use cylindrical structure only, because obviously cylindrical structure gives you a higher mechanical stability. So obviously, depending on the suspensions and other things, obviously there is a vibration inside the battery pack. So obviously for that purpose, cylindrical will be the best choice for two-wheelers. And I think that pouch should not be used in any cases, in case of EV, because there is a huge vibration happens when actually we are running more vehicles, right? So because this doesn't have that much high, means mechanical stability, we should not use pouch structure, right? And obviously the pack efficiency is nearly medium in case of prismatic, means prismatic is in the medium range, right? So I hope you can understand that how actually you can choose a cell form factor depending on your application. So obviously, see, battery technology is not we are using in only in EVs, right? There are multiple industries are there. There is a medical industry, there is a consumer electronics industry, there is a solar industry, right? So depending on your application, actually, you have to choose this type of cells. Now we are going into the cell, how lithium ion cell life degrade actually. So one of the students asked me yesterday that why actually we are replacing the cells. Means obviously multiple, after multiple charging, discharging, why actually we are means replacing the cells, why we are not importing the cycles, right? So it is not possible. Obviously there is a means everything can't be possible, right? We manufactured already, you have means in these slides, actually in the previous slides we have seen that how actually we are manufacturing the cells. So in case of cylindrical, in case of pouch, sorry, in case of prismatic, it is impossible, right? So obviously we have to do a new manufacturing process. Now, what are the points, what are the features, we can say what are the criterias, right? That actually increase the lithium ion cell life degradation. Now on the right hand side in the graph, you can see that actually this is a means practical data which I have done. So this is basically a NMC data, NMC, right? So nickel, manganese, cobalt. So you can see that the discharging current, you can see I have mentioned here, that is discharge with CC, means constant current. CC means constant current at 1 ampere. Cycle condition, you can see that means charge cycle condition, that is CC CV, constant current, constant voltage. That is also done by 1 ampere. And you can see that I charge up this cell up to 4.2 volt and I discharge this cell up to 3 volt, right? So 3 volt is a very good. At 3.3, actually the NMC cell already discharged full, nearly 1 to 2%, but I use more, means lower one, right? 3 volt. So you can see how the cycle life degrade. At 0 cycle, there is a residual capacity that we are getting. Actually, I have taken nearly 2000 mAh cells. I think, yes, that was 2000 mAh cell. And 1 ampere, that means 0.5 C I have taken. So at 0.5 C rate, we have started a cycling test and we named it as a aging test of a cell. So whenever we are choosing our cells, we do this type of testing, aging testing. Whatever the cycle means they actually have given on the data sheet, is it absolutely matching or not? To verify this, obviously we do this type of aging test. You can see guys that after 300 cycles, it is up to 80%. Means suppose I am using a 2000 AH cell, a 2000 milliampere hour cell, and after 300 cycles, suppose I am using this cells in a mobile phone, right? And every day we are using mobile phone, right? Every day we charge and discharge, right? And one cycle means obviously there is a full charge and full discharge. That means one cycle, right? So if we do this type of cycles on a daily basis, means it will long last, means less than 1 year, right? Means 2000 milliampere hour at the initial state we are getting. After 300 cycle, we are getting only 1600 mAh. That is 80% of that capacity, and it is obviously decreasing day by day. Suppose I have not taken here more number of cycles because see, please be noted, whenever a lithium ion battery is on 80% residual capacity, after that it is very harmful to use this type of cells because anything means can happen. It may be a thermal runaway, it may be blasting, it may be any type of gas ejections, right? It means 80%, up to 80% it is safer, but below 80% it is not safe to use this type of cell. Means it may be NMC, it may be LFP, but we should not use below 80%. So that is why nowadays in EV, I means you have seen that this terminology we are using, you can see your battery health. You can see your battery health. right? We have that type of softwares, that type of, we are using algorithm that you can get a very much accurate battery health. So why we need battery health? So obviously you can use after 80% as well, but there would be a risk factor, right? So that is why in the BMS itself, we are actually means doing some kind of algorithm that to get this type of state of health, or we can get the residual capacity. So that is a BMS work, right? So this type of state of health actually we are displaying, right? So obviously it is a safety concern for a user also. So user should get this type of data. Now what are the factors? The first factor is a formation of dendrites. So what is dendrites? Now first you can see that which are the main cause of this type of dendrite formation. One is the fast charging. So we are always try to implement fast charging, right? In everywhere. In India also we are means just doing this fast charging station. We need fast charging station. But yes, in every fast charging station, most of the time, every EV manufacturer recommend that you should first charge your battery from 30% SOC to 80% SOC. If suppose your state of charge means battery charge is less than 30%, you should not charge uh, with fast charging, right? And also same as for if your battery having more than 80% charge, you should not use fast charging because it would actually damage your cells. So obviously that is the main reason of the formation of dendrite in a lithium ion technology. Means it is same for NMC as well as LFP, right? So also there is a second point, that is cold temperature charging less than 0 degree, and obviously electrolyte properties. So these three are the dependencies. Now what is dendrites? This is basically a needle-like structure. Lithium is a metal, right? So whenever this type of we can say fast charging, cold temperature charging we are doing, on that case, this type of needle-like structure is actually developed inside the anode, especially. So you have to keep in mind where actually, whenever we are actually charging, the lithium ion is flow from cathode to anode, right? Cathode to anode throughout the separator. So on that case, obviously, there is a anode is actually collecting the lithiums. So on that case, on the anode side, actually, this type of pyramidal structure you can see, it is developed, and obviously it is because of uneven lithium deposition. This is why, that is why actually this type of pyramidal structure or needle-like structure actually we have seen in the anode side. And what happens due to this type of charging, for suppose 50 cycles, 100 cycles, 200 cycles, so it would actually damage the separator. And as you know, if we damage, why actually we are using separator? To separate the cathode and anode. Otherwise, it will be short circuited. So obviously, formation of dendrites actually hamper the separator. So that is why it will cause internal short circuit. So that is the main reason we should not fast charge our battery pack whenever the SOC is above 80% and below the 30%. The second one is a one second, guys. So the second one is the loss of lithium ion availability. Now what happens? Whenever actually we are doing this type of charging, discharging, right? Obviously, we know that lithium ion moves from cathode to anode during, obviously, and vice versa, during charge and discharge. So only lithium ion is moving from cathode to anode and anode to cathode. The electrons obviously flowing through the external circuit. So over the time, what happens? Lithium get trapped in unwanted reactions. It may be in the anode, it may be in the cathode. Basically, ACI layer. So in the right hand side block diagram, you can see that anode side. So mostly we are getting the problem started from anode side. So you can see that is a normal initial ACI layer, solid electrolyte interface. ACI means solid electrolyte interface. So this is the layer structure. After so much means charging, discharging, I am talking about normal discharging, charging. After why actually after 100 cycle, the capacity is decreasing. After 200 cycle, capacity is slightly more decreasing. After 300, it is more decreasing because the lithium is more trapped in the anode. Right? I hope you get my point. Lithium is more trapped into the anode. Now, what happens if lithium is trapped? So obviously lithium ion is decreasing. So on that case, your overall capacity would decrease. So obviously it would actually capacity loss, right? So this is named as lithium plating as well. We can say this is as a lithium plating, right? So these are also, means this point is also a major concern to degrade a lithium ion life. The third one is a electrode degradation. So that is not actually directly connected with the lithium ion, but it is connected with the aluminium and copper electrode. So obviously we are using metal electrode, right? We need obviously, because whenever we need to collect the current, we have to use copper or aluminium. So on that case, whenever actually we are doing high charging and discharging rate, right? So it actually give a mechanical stress and it is day by day increasing. So if suppose we are doing deep discharge means suppose we drain the battery below 20% every cycle. In every cycle, suppose we are, mean in case of cell phone batteries also, suppose every day means suppose you are having two cell phones, right? And one cell phones you daily means both the cell phones you are charging and discharging on daily basis. One cell phone you are discharging up to 0% and one cell phone you are discharging up to 20%. So obviously you can observe that 0% discharging phone will means obviously will lose its capacity very short time, like in a very short time. In supposed to be 200 cycle, 150 cycles, the cells will be damaged, right? And for 20%, obviously, it will long last. So that is why actually always we recommend that please put your charger means whenever the battery pack or the cell charge state of charge will be at 10% or 15% level. And this type of phenomena means electro degradation happens whenever we are doing overcharging, supposed to be greater than 4.2 volt. So it basically damage the cathode structure. So these are the main points that you can see that in every degradation points, there is a one point is very common, that is high charge discharge rate. These are very common in every points, right? Now electrolyte breakdown. See guys, whenever actually we have seen lead acid, right? And you have seen that whenever actually multiple times we are charging and discharging lead acid battery packs, on that case the internal electrolyte, not electrolyte actually, the water actually vaporized, and on that case we have to put again a deionized water to basically get those battery means on its actual conditions, right? But in case of lithium ion, it can't be possible because it is means not maintain, means we can't do the maintenance, right? So due to this type of high temperature charging or discharging, as we know, electrolyte is a gel type technology actually we are using. Means nowadays also we are using gel type technology. So during this high temperature charging, the electrolyte actually reduced and oxidized, right? So it actually causes decomposition. So in case of charging only, actually, we have seen this type of phenomena. And if the temperature is more than 40 degree. So what happens actually, electrolytes, actually it actually affects in the internal resistance. Means whenever the electrolyte actually, see, why actually we are using electrolyte? Come on, guys, why are we are using electrolyte? To basically flow the lithium ion from anode to cathode or vice versa, cathode to anode, right? So that is the main work of electrolyte, right? So if the electrolyte is decreasing, then obviously lithium ion can't move properly. So it will impact in the internal resistance buildup. So as a result, the internal resistance will be increased. And what does it mean? Internal resistance increased. So obviously there will be a loss, right? If there is a resistance and we are flowing the same current, so obviously there will be a heat loss, that is I square R. So whenever actually your battery is degraded, supposed to be there is a electrolyte is vaporized or reduced or oxidized, right? On that case, if you do same, if you apply same amount of charging current or discharging current, you will observe that the cell is heated up more. And obviously above 60 degree, there would be a chance of thermal runaway. Whenever the thermal runaway starts, actually it will actually it will make a fire cases, right? So that is the main thing actually. Whenever we are using this type of lithium ion batteries, means we should means there should be a proper state of health monitoring system, right? And it would be available on the display, means any kind of EV that would be, maybe two-wheeler, maybe three-wheeler, maybe four-wheeler. So every user should be able to access the state of health, right? It is very, very important. Okay. So basically, so these are the points actually I have already discussed, that are the points why the lithium ion degrade. Now actually I will be sharing with you, 1 second, the BMS, how the BMS actually works. One second, guys. Okay, I hope you can see my screen. So what is battery management system? So we have seen all the things, right? High charging current, over voltage, right? Overcharging, under voltage, or it can be maybe deep discharge. So how to control these things? Cell doesn't have any circuitry. If we are using a raw cell, it doesn't have any kind of circuitry, right? If you are just loading up a cells, I'm talking about a single cells, not a battery. If you are loaded up with, it may be some resistance, a LED, or anything, any type of load, it will be actually drain up to 0 volt and it will be damaged. The cell will be damaged. So obviously it doesn't have any protection circuits internally. Means if there is any kind of high charging voltage applied through the cells, obviously it will be damaged because it doesn't have any type of protection, right? Voltage, this doesn't have any voltage level protection, any current level protection, any temperature level protection. So that is why actually we implemented battery management system. So in battery management system, these are the key points that actually we covered. The first one, that is the overcharge protection. Already we have seen that most of the NMC battery pack having 4.2 volt maximum. Above 4.2 volt is riskier thing, right? So how to protect from over 4.2 volt? So in BMS actually, there is a voltage sensors actually we have used. I will show you hardware architecture, means what are the parameters actually we are using, what are the sensors basically we are using inside the BMS. But the purpose to use this type of sensors or everything is for overcharge protection. That is nothing but over voltage protection. The second one, it is over discharge protection. That means under voltage protection. So most of the time we suppose there is a 5%, 10% state of charge. So that is on state of charge level. And we are setting up these things, this type of protection in voltage level. Yes, we do have that type of algorithm to set in SOC level also, right? That is residue, means there is a depth of discharge. So that are the different thing. I will be covering up those things also. So over discharge protection means there is a under voltage lockout. Means whenever suppose we have set it the voltage as a 3 volt. And in a battery pack, there are multiple cells actually we are using, right? Series, parallel, combination. And most of the time we actually use to measure series combination cells, not the parallel combination cells, right? Means suppose there is a battery pack we are designing. There is a suppose 10S. 10S means 10 cells connected in series, and suppose 10 cell connected in parallel, right? So okay, before that actually, okay, no issue. In the battery pack design, obviously you will be cleared. Means obviously I actually have a question for you guys. Means whenever actually we are seriesing the cells, so what actually happens in the voltage level? Obviously it will sum up, right? Whenever we are supposed to means we are doing parallel connections, what actually you will adding up? The ampere hour, the AH. So in series connections, we are adding up the voltage. In parallel connection, we are adding up the capacity. That is in ampere hour. So that is the main fundamentals. Now, suppose we have 10 series combination as well as 10 parallel combination. Then how many total number of cells we are using? That is a question for you guys. Suppose we are having 10 series number of cells as well as 10 parallel number of cells, or we can say 10 cross 10 that we are using. So what would be the total number of cells? Please guys, answers. Yes, 100. That is a correct answer. So means each series combination having 10 parallel cells, right? So 10 parallel, again there is a 10 parallel, again there is a 10 parallel, right? So we are actually, whenever actually we are connecting BMS, we are sensing the parallel voltage, parallel cells, right? So whenever we are paralleling two cells, obviously the voltage would be same. Mostly whenever actually we are designing a battery pack, on that case we actually choose same milliampere hour, same voltage, same capacity, same IR cells, right? We suppose we are designing a battery pack where basically we are using 500 number of cells. Every 500 number of cells should have same capacity, same voltage level, same state of charge level. Means I am talking about single cell. Every cell should have same state of charge whenever we are actually manufacturing or producing a battery pack. Same capacity, same SOC, same voltage level. That's it. That four things actually, you same IR, same internal resistance should be there. So there is a very less tolerance actually we are giving, roughly around 0.1%, roughly 0.1 to 0.5%. Because whenever actually we are increasing this tolerance, it will actually give you a means faulty data, right? After suppose 100 cycle, it may be imbalance you have seen. So that is why best practice is to take a very low tolerance, 0.1 to 0.5% tolerance. Otherwise, your battery will be malfunctioning. Means you can see that one cell is overcharged, one cell is suppose to be in normal level. Suppose one cell in 4 volt and another cell is 4.2 volt. So obviously when a 4.2 volt BMS sends, we already programmed a BMS at 4.2 volt, right? So suppose 90 cells are at 4 level, 4 volt level, and suppose 10 cell, right? 10 cells suppose at 4.2 level. So obviously there is an imbalance between the cells. That means one cells is fully charged, but another 99 cells is not charged that much, maybe 90%. But whenever BMS sends that one cell already reached 4.2 volt, immediately they will cut the charging, right? They will cut off the charging. So that is how actually BMS works. So obviously this is used for a safety, but whenever actually you are designing a battery pack or are manufacturing a battery pack, on that case, you have to keep in mind these 4 parameters should be same. And there is a very less tolerance up to 0.5%. Now there is a third protection, that is overcurrent protection. So obviously if the charging current is more than a recommended charging current, so BMS will cut off, right? Suppose we are using this X battery pack and we are using Y charger, right? So there should be a compatibility, right? In a battery pack, suppose it is written, please use 20 ampere charger, and you are putting 30 ampere charger. So obviously it will cut off. If suppose there is no BMS, this 30 ampere charger will damage your battery pack, right? Obviously we are giving 20 ampere, so that obviously makes sense, right? Why actually we are giving 20 ampere? Because you can see from the data sheet itself, right, that every manufacturer gives 0.2 C, 0.3 C charging. Slow charging will be the best charging, guys. So that is why actually this type of current level protections also we are implementing inside the BMS. So BMS having current sensors. So by using current sensors, actually we sense the current and obviously do accordingly. So obviously if there is a over current protection, obviously there would be a short circuit protection. So what is the difference between two things? What is the difference, guys? Any idea? Over current protection and short circuit protection. So obviously if there is overcurrent, there should be short circuit, right? I mean, what do you think? So basically overcurrent means, suppose your current you are limiting at 20 ampere and you used a 25 ampere charger, right? You are actually using 25 ampere charger. The main difference between short circuit and overcurrent is in the delay time and what is the rate of change of current at instant of time. So that is the main difference. So you are supposed you are applying 25 ampere and it will actually sense for suppose 1 second, 2 seconds. After that it will cut off. But in case of short circuit, for a microsecond or millisecond time, the current could be infinity, right? It would be more. So that is why short circuit protection is means if you have overcurrent protection but doesn't have short circuit protection in your BMS, then obviously it will damage your battery pack, right? Because very small means time, very small instant of time, actually this type of short circuit happens, right? It in microsecond, milliseconds. So that is the difference. There is a temperature monitoring system also are there. Means we are using temperature sensors to basically sense the cell temperature. So obviously if there is a multiple cells we are using, we should have multiple temperature sensors. And there is a technique that is cell balancing we are using. So mostly we used passive cell balancing. Now there is a two type of cell balancing actually we are using. One is active cell balancing, one is passive cell balancing. So what does it mean? Means what is a cell balancing technology? Suppose we are manufacturing a battery pack. At the initial state, we think that we use all the identical cells. But as you know, every cells would not be your identical, right? So after doing charging, discharging, charging, discharging, after supposed to be 100 cycles, it may means obviously it will happen that one cell charged easily, or we can say suppose one cell is at 100% SOC, another cell is at 95% SOC. So the cell imbalance actually occur. So whenever there is a cell imbalance, what this cell balancing circuit will do? So whatever the cells having higher voltage, or we can say higher capacity, means sorry, higher state of charge. So it will discharge those cells, right? That is a passive balancing, and it will not affect the low charge cell. So there is a two cell. Suppose there is a two cells. One is a higher charging cell or one is a lower charging cell. So the lower charging cell will be fixed, but the higher charging cell will be discharged through a resistor. There is a resistor network we are using in passive balancing battery management system. So obviously you are losing energy, right? Yes, we balanced the cells, right? We balanced the cells, but we are actually losing energy. In case of active balanced BMS, what actually we are doing? We are using these cells. Suppose these cells having higher energy. We are extracting the energy from the higher cells and we are delivering the same energy to the lower cells. So here actually we are utilizing the losses. So that is the main difference between active balancer and the passive balance BMS. But there is a huge difference between cost, right? In case of passive balancing, we use only a small resistors basically, and there is a heat loss happens. Whenever actually we are using active balancing, mostly we have to add capacitors. Whenever means obviously there is an algorithm will be there, but in a hardware point of view, actually we used bulky capacitors. So capacitors will charge from these high cells, and same obviously you know that there is a capacitor property, right, to hold the charge. So it will discharge to the lower charge, means obviously lower SOC cells. So that is how actually active balancing and passive balancing works. And beside this, we have two major components, that is SOC, means state of charge calculation, and another one is state of health monitoring. So these two are very important in case of EVs. See, in mobile phone, we have seen that the SOC is there, but we have not seen the state of health, right? Means after 1 year, obviously you will not get the same backup from the mobile phone. After 2 years, it will be decreasing, right? So day by day it will be decreasing, but you would not get the battery health, means how much residual capacity actually remaining on that state. But in case of EV, it is required, because in means you are not getting warranty on mobile phone, I think more than 1 year, right? But EV manufacturer giving 8 years of warranty. So obviously they have to measure the state of health of the battery in every stages, right? So that is the work of BMS. Mainly it is a software, means in the algorithm actually we are using state of health monitoring. And there is a communication system. In EV, there is a multiple components we are using. We are using battery, we are using power electronics controller, we are using motor, right? We are using thermal management. Also we are using other control units as well. So basically I am not talking about only EV. In IC engine based vehicle also having their own communication system, right? So whenever actually we are supposed to be implementing a EV, right? So battery also have that communication system. Means whatever the battery voltage, whatever the internal current, internal temperature we are monitoring, that should be transferred to the charger, right? Charger is a different circuit, battery is a different circuit, motor controller is a different circuit. So each circuit should have communication with each other. So BMS in EV industry, basically we use CAN communication. So obviously I will take a separate session on CAN communication and I will show you a real life CAN data, right, which we have developed for our one of the customers basically. So I will be showing that data also. So basically in EV, we are using CAN protocol. So that is the mode of communication actually we are using in EV to communicate with charger, to communicate with any kind of IoT system, right? Uh, Obviously, traction inverter controller, also DC-DC converters. What are the control units are there? We are actually communicating with each other. So that is also an important factor. So that is also a software-based model. Yes. In the hardware, obviously, we have to use a CAN IC. So there is a separate CAN ICs actually are widely available in the market. So we are incorporating those ICs in the BMS. Now, basically, I want to show you the BMS hardware architecture. So what are the major components actually we are using in BMS? So the first one, that is AFE, that is analog front end. So you can see that this block, this huge block, that is an analog front end. So by using analog front end, actually in analog front end, what AFE actually does? It actually get the actual data, means there is a voltage sensor, means it is a basically voltage sensing circuit. So it actually senses the voltage, and after sensing the voltage, it just convert this analog data to a digital data, like in 1-0 format, and it just pass this data to the microcontroller unit. So obviously there should be a microcontroller unit, right? But there would be some hardware arrangement to sense the actual data. So everything, see here the main three component we have to sense. One is voltage, one is current, and another one is our temperature. So everything is sensed on a voltage level only. So how can we sense current as a voltage? How can we sense? This is a basic electronics, guys. Means we are using a shunt resistor. So whenever we use a shunt resistors are actually in a very low resistance actually we are using. Supposed to be 1 milliohm, 2 milliohm. So whenever there is a drop, right? Whenever suppose there is a 100 ampere is flowing through this shunt resistance, there is a drop occur, right? So we are sensing those drop and we are actually calculating the data from the drop. So there is another circuits also we are using, op-amp circuit actually we are using to basically implement those drop in an actual voltage level, because drop are also in the 1 millivolt, 2 millivolt drop actually we have seen, right? So because of high accuracy actually we are using a op-amp circuit to basically means amplify the voltage level. Basically MCU actually can read means up to 3 decimal places, means it depends on their ADCs. So that is totally a hardware embedded part, means whenever actually we are having a MCU, we have to select a MCU for BMS applications. Then first we have to keep in mind that one cell voltage means 4.2 volt we can measure, right? So we have to measure up to 3 decimal places, means 4.123, that is. So obviously most of the manufacturer actually use 3 decimal places. If suppose we are using a very upgraded microcontroller unit, they also can use 4 decimal, 5 decimal places as well. Because of temperature actually we need a more accurate data, right? 27 point something. Basically for current data actually main we required. So it may be a BMS can sense 100 ampere, as well as the same BMS can sense 0.1 ampere also. So that is why we have to use that type of MCU, means ADC levels. Basically in BMS we are not using the MCU ADC level. Already all the data is converted from analog to digital by using this AFE. And you can see guys that here basically the resistance banks actually you can see there are multiple resistance actually we are using, right? So this is basically used for passive balancing. And you can see there is a cells actually we are connecting, VC0, VC1, VC2, VC3. So all the cells you can see that connected in series. So BMS is only used for series cell balancing, not the parallel cell balancing. Because whenever you will connect two cells in parallel, suppose one cell is having high charge, one cell having low charge. So it will automatically balance the charge whenever you are connecting in parallel. But whenever you are connecting in series, so obviously there is one positive tip left, one negative tip left, right? So if you connect positive, negative each other, so obviously it will be short circuited. So that is why in series combination of cells, actually, this type of imbalance occur, right? In case of parallel, we do not need that type of balancing. But yes, if suppose you are not designing in a proper manner, if you are not manufacturing in a proper manner, then parallel cells will actually give you the pain. So I have actually seen those pain. Means if you are not designing a battery pack properly, and means there is a malfunctioning happens in the parallel grouping, then it will actually damage the overall system. So that is the main thing. In BMS, the main control thing is the MOSFETs. That is a power switch. So here basically you can see that is a symbol of MOSFET. So mostly we use MOSFET, mostly you use MOSFET for controlling the path. So whenever suppose we are charging, the MOSFET is in turn on state. And whenever suppose we need to cut off the charging, so we are actually turn off the MOSFETs. So then these MOSFETs are actually driven by the microcontroller unit. So all the data we are calculating inside the microcontroller. So obviously we can give the command to the MOSFETs, and obviously depending on that command, the charging will stop, as well as the discharging also we can control by using these MOSFETs. So that are the major components, that is AFE already done, MCU, that is microcontroller unit, CAN IC, that is for only used for communication purposes, MOSFETs for controlling the power path, shunt resistor for measuring the current, and NTC, that is used for sensing the temperature. So these are the main components which actually we are using inside a BMS. And that is the overall architecture on the screen you can see. Now let's come to the parameters. These three parameters are very, very important for us. That is SOC, SOH, and DOD. DOD means depth of discharge. Suppose our mobile phone, I think that is a very means it is the only example that you can understand very easily. Suppose our mobile phone having 1% battery charge, right? 1% SOC, state of charge. And after 0%, suppose it is switched off, totally switched off. But whenever we are trying to switch on, at least one time, they will glow the battery, right? Means, sorry, display. At least they will glow your display. So that means there is some charge already have inside the battery, right? Cells I am talking about. In the mobile phone, I think you may have seen this type of phenomena, right? After 0%, after switch off also, one or two times the mobile phone may switch on again, right? The actual SOC is not 0%. That is actually your DOD, right? Depth of discharge is maybe in SOC, means in BMS internal data or internal parameter, that is only 5%. So that means DOD is 0%, but SOC still having 5%. So that is how actually we are designing a battery pack. In case of EV also, so I don't know, I think my Zoom is disconnected. Okay. I hope you can let me share the screen again. So I was talking about the SOC, SOH, and DOD, right? So there is a what I told. So depth of discharge and SOC. Suppose your battery pack having or your mobile phone cell having 0% SOC. 0% SOC, as we can see the 0%, but actually that is DOD, depth of discharge. But still there is a 5% SOC available in your mobile phone. So in case of EV also, actually we designed in such a way. Suppose we are having 100 ampere hour. So that is 100 ampere hour obviously. So depending on 100 ampere hour, we are having our SOC, state of charge. But I want that up to 10% it should be discharged. Below 10% should be reserved, right? Please be noted, up to 10% the battery should discharge, but below 10% it should be reserved. So whenever we programmed in such a manner inside the BMS. So BMS will show you the DOD data, means whenever it is the battery is decreasing, charge is decreasing up to 10 ampere hour, your actual SOC which is actually displaying in the screen, you can see that is 0%. But actually 10% is in reserve condition, right? So that is SOC, that means see releasable, the total releasable energy. But DOD means see released, whatever the power or energy we have released. So most of the time actually, whenever suppose we are having a SOC of 100 ampere hour, right? State of charge, which is if we measure this in capacity basis, so 100 ampere hour we have our battery pack capacity is. But we set 90 ampere hour as a DOD, means up to 90 ampere hour it should be discharged and 10 ampere hour should be in reserve for some emergency applications, right? So that is the difference between SOC and DOD. And SOH obviously that is the C max by C rated into 100%. So this obviously whenever we are doing cycle by cycle, so this SOH data is changing. So there is a lot of various type of algorithm actually there. Whenever suppose we are using this type of means we are calculating the SOCs. Now, okay, there is a SOC estimation technique that is OCV based, means open circuit voltage based SOC estimation technique. So what does it mean, open circuit voltage? See, I already have shared with you one means OCV versus SOC data. So on the screen on the right hand side also you have seen that. So there is a basically NMC data actually I have taken, nickel manganese cobalt. So NMC having a linear characteristics. So during charging, during discharging, you can see there is a linear. So from 10% you can easily predict, from 20% you can easily predict by using the OCV technique. Suppose you are having a voltage and you are having a multimeter. So by using the multimeter, you can actually take the open circuit voltage and you can predict the data, means state of charge. Suppose the voltage is 3.7 volt, then easily you can take a call that the charging is about 40%, right? So for NMC, it is possible, but for LFP, it is not possible. So on the left hand side, you can see this is a LFP data. So in case of LFP, actually, you can see the voltage is absolutely stable, or we can say constant from 40% to 60% capacity. So how can we predict? In this OCV model, suppose you are using a multimeter and you are checking the voltage as a 3.3 volt or 3.2 volt. You can't predict the SOC. It may be 30%, it may be 60% as well. So that is why OCB based SOC estimations actually give a wrong data for LFP chemistry. So that is why it actually initial state OC means SOC estimation technique. Initial SOC estimation. Suppose we manufactured a manufacturing a battery, and for the first time we are suppose connecting a BMS. On that case, yes, it will predict a rough data depending on OCV, but it is not the actual solution. So what is the actual solution? So see, this is the advantage and disadvantage of this type of techniques. You would get accurate result under rest, but obviously that is for NMC, not LFP. Very simple hardware, you only need a voltmeter, right? You have to measure, means you need a voltage sensor, no need of current sensor. No drift, means if there is obviously means drift, it may be on the voltmeter or the voltage sensor, but most of the time there is no cumulative error actually occur. If I'm talking about this 300 cycle, 400 cycles we have done, on that case, the SOC level is rapidly actually decaying or increasing whenever the cell is aged for 200 cycles, 300 cycles, 400 cycles. So that is actually the main thing, that whenever actually we are using battery, suppose battery is in degradation, so your OCV actually changes, means your voltage data actually changes during a cycle by cycle. And it is not a real-time data, means it is not possible to sense the open circuit voltage every time, right? Whenever suppose you are running your EV, and it is can't be possible to measure all the time this type of data, right? Now the second technique, that is Coulomb counting technique. So most of the manufacturer actually use Coulomb counting technique, means obviously we use OCV technique for a initial calibration only initial state. But this type of Coulomb counting actually we required, means that is nothing but a AH counting. We need a current sensor and we need a clock basically. So obviously, whatever the current actually we are supposed to be delivering, or suppose it is under discharging or charging condition, we can actually count those current. And as we know the ampere hour, obviously we have a cell. Suppose 5000 milliampere hour, that means 5 ampere hour, right? So suppose we are counting the time as well as we are counting the suppose ampere, right? So suppose we are having 5 ampere discharging current. So in 1 hour, so it will be discharged 5 ampere hour. So obviously we can predict the SOC as well, right? For a 5 ampere hour data, if there is 2.5 Ah, in a 5 Ah cell, suppose we discharge 2.5 Ah, how much percentage it would be? 50%, obviously. If suppose my ampere hour, I am measuring that 1 ampere hour, right? So that means 80% already charge available inside the battery. So that is how Coulomb counting will make more sense. But yes, this type of technique also have a disadvantage. So there is, suppose there is in current sensor, there is a small difference. The actual current is suppose 1 ampere, but your sensor data is sensed it as a 1.01 ampere. So over the time, this 1.01, just 01, will actually change the game, right? It will, these small errors actually accumulate, right, over time. So that is the main disadvantage of this type of Coulomb counting. So you have to be, whenever suppose you are selecting a shunt resistance, the shunt resistance should be more precious, right? Means you need to measure a proper voltage, means voltage drop, right? If suppose there is a tolerance in the shunt resistance, you have to put those tolerance level inside the algorithm, right? You have to means you have to code in such a way that you have to means whatever the drift actually is there, you have to overcome over time. So basically that is a disadvantage. But yes, the advantage, it is simple, very simple and fast. By using a MCU it can be possible. And real-time capability that works during dynamic operation. Suppose whenever we are charging We can predict the SOC depending on the current rating. We can predict the whenever suppose there is a loading condition, right? On that case, obviously we are counting the ampere hour, so we can easily predict the state of charge, right? Now, suppose we are doing only Coulomb counting, not not a voltage based option. Then what happens? Mainly, suppose we have a cell, right? And there is a suppose 300 cycles we covered. So after 300 cycles, what happens? Its capacity will decrease, right? Suppose we are using a 5 ampere hour cells, and after 300 cycles, its capacity is decreasing. Maybe suppose 80%. So that means what would be its actual capacity now? That is 4 ampere hour, right? So initially it was 5 ampere hour. After 300 cycle, it is 4 ampere hour. That means the cells can charge up to 4 ampere hour and can discharge up to 4 ampere hour only. So obviously there is a gap of 1 ampere hour. So it will not predict the actual data, actual SOC. So for that instant, we need the voltage data as well, right? So that is the main implementation in the Kalman filter SOC estimation technique. This is very new. Kalman means this is a very new estimation technique actually we are using nowadays. From the past few years, actually, we have implemented this Kalman filter algorithm. So that is a very means new algorithm and also a very complex algorithm, because we used both the datas. S means obviously we are having ampere hour data, right? Means we are counting the current over time, as well as we are having the OCV model. So in every state of means we have to do a aging, right? We have to do the aging, and suppose a 50-50 cycles aging we have done. We have to put those data. Means after 50 cycle, the OCV has changed. After 100 cycle, the OCP has changed, right? So this type of data we have to implement inside the algorithm, as well as we have to implement the Coulomb counting also. So that is how, by using this both algorithm, actually we can predict the actual state of charge after 300 cycle as well. So that is the main advantage of this type of algorithm. Means over the time, actually it will give you a right data, but in case of Coulomb counting, over the time actually it will not give you the accurate data, right? So I hope you can understand. See, this is the overview. Means whenever actually you will be getting into this type of industry, you will get the actual depth, right? Means the software engineers are focused on the Kalman filter, that how actually we can predict the datas, how we can get the OCB data of each cycle. I am talking about 50 cycle, 100 cycle, but there would be a 51 cycle, there would be a 52 cycle, and every cycle will affect, right? So it is very, very complex to design this type of SOC estimation, right? So obviously the advantage would be accurate, real time, and robust. For lifetime, actually, we can use this algorithm, but it is very, very complex. Okay, so this is basically we have done this thing. Okay, there is some question, I think. Let me see the questions, guys. Okay, there is a full form of DOD, SOC, and SOH. Okay, the full form of DOD is depth of discharge. Depth of discharge is a DOD. SOC is state of charge, and SOH is a state of health. So that is the full form. There is a question. Okay, what will happen if BMS fails during operation? So obviously, if your BMS fail, your battery will fail, obviously. We have seen many this type of battery pack which have short circuited, because of BMS failure. It may be deep discharging will happen. Deep discharging means the battery voltage is zero. A 200-volt battery giving a 0 volt because BMS under voltage cutoff not works properly because of malfunctioning. So obviously, if your BMS fail, but yes, voltage is okay. But whenever there is a current, suppose there is a high short circuit current or short circuit happens on that time, actually, we use some safety features. Safety fuse actually we are using whenever designing a battery pack. So there are multiple things actually we are incorporating in designs. So I will show you that how actually we are designing a battery pack. There are other factors are also there. If BMS fails, then actually we can at least warn the user that there is an emergency, right? So that is how actually we are designing a BMS, sorry, battery pack. Okay, now let me start with the battery pack, battery technology. Okay, guys, let me share my screen again. So guys, I hope you can see my screen. So from the on the screen, actually, you can easily understand that how actually cylindrical cells, by using cylindrical cells, actually, we are making a battery pack, right? From the image itself, I think you can understand. How you can understand, guys? I have not told anything. Okay, so this is basically a three-wheeler battery pack. So on the right hand side, this is a, we can say, a 3D model of a battery pack. So what are the major components actually we are using? So on the right hand side, the main component is started with cells, right? That is the primary component. So there is a cells we are using, and can you guys guess which type of cells it is? On the starting itself, we are started these sessions with this type of cells. This is basically a prismatic cells. So prismatic cells are already, I told you that the prismatic cells are widely used in EV. So basically this type of prismatic cells we are using, and we are using 16 cells in series, means 50 nearly 51 volt, and LFP chemistry we are using. Mostly for three-wheeler battery pack, we are using LFP chemistry. So 3.2 volt into 16, if you do, then you will get 51.2 volt, 100 ampere hour battery pack. So we are not doing any parallel operations here. We only do series operation. Means 16 cells, only 16 cells is connected in a series manner. And we are connecting a BMS, you can see. So basically this is the outer casing. That is a mechanical outer casing we can see, and there is a cold plate, there is a base plate basically to hold the battery pack, and you can see that in between each cells we are actually placing a insulation pad. So this is because of safety purposes, actually we are using the insulation pad. Most of the EV manufacturer, battery manufacturer, I am especially talking about three-wheeler battery manufacturer. Because of the cost-centric market, they are using just a FRP sheet, a plastic, means insulation type of sheet. But good manufacturer always use a thermal pad. That is a passive thermal balancing technique that they are using. So you can insulate this type of cells by using insulation pad as well as the thermal pad. But insulation pad cost roughly 10 rupees, and the thermal pad of same size will cost nearly 300 rupees. So that is a cost difference between these two things, a thermal pad and a insulation pad. That is a FRP sheet. So that is we are using to basically give a insulation between the, also we have to do for thermal extraction as well. means heat extraction as well. Now you can see there is a BMS already. There is a bus bars actually we are using to connect the cell positive terminal, negative terminal. So there is, whenever we are connecting this as a series, right? So series means obviously there is a positive, negative, right? And parallel means all the positives are connected with each other, all the negatives are connected with each other. Once again, I think I have. Okay. So this one. See guys, so whenever we are doing the series connection, so we are actually in the upper one, that is a series configuration. So one cell positive is connecting with another cell negative. One cell positive is another cell negative. But you can see that there is a one final positive and one final negative actually we are using, right? And we are supposed to be using 3.6 volt. So four cells connected in series. So that will give us a 14.4 volt 3400 mAh. Suppose we are doing a parallel configuration, then all the positive cells are connected in, means obviously connected with each other, and same as the negative. The voltage is same, but the current is increasing, the mAh, right? So there is some question. So you're talking about Kalman filter. See guys, Kalman filter means, already I think you understand, right? OCV and means open circuit voltage technique, and obviously our Coulomb counting technique. So why actually we are implementing this Kalman filter? Basically, whenever suppose we are doing ampere hour counting, on that case what happens after suppose 100 cycles, 300 cycles, 200 cycles, actually we are unable to match those ampere hour rating. So obviously it will give you a improper state of charge. Mainly this is used for state of charge calculation, right? So suppose your battery pack having actual 40% SOC, but it will show you a 60% data. So what happens actually, whenever suppose there is a 10 cycle we are doing, right? We have done 10 cycles. So your OCV would change, means your open circuit voltage of in each SOC level will be changed, right? So at suppose you are starting with your first cycle. So in first cycle you will be getting a OCV data. SOC versus OCV means state of charge versus voltage data, right? For your cell. After 50 cycles, it will be changed. Your voltage level will be changed. After 100 cycle, it will be changed. Means it will rapidly discharge, right? After 300 cycle, from 4.2 to 4.1 volt, right? It will rapidly drop. From 4.1 to 3.7, it will rapidly drop, right? So in between the ampere hour change, the voltage will change rapidly whenever we are doing more number of cycles. So actually means Kalman filter, we are implementing the OCV data, and we are actually assuming the OCV data over the cycles. Suppose one cycle done, we changed the OCV. After one cycle done, we changed the OCV, right? Every 2, 3, 4, 5, 10, 50, 100 cycles, actually we are means changing the OCV data. So it is a rigorous process is going on inside the algorithm, right? And we are actually after 100 cycles we can actually predict the proper data, right? So that is how we are actually changing the OCV model, as well as we are counting the ampere hour also. So that is the main purpose of Kalman filter. Okay, why battery aging happens as we use it for 2 to 3 years? So already guys, I told you that that is a property. So mostly in case of mobile phones, electronic gadgets, home appliances, everywhere we use NMC cells because of high energy density. We need a lighter mobile phone, right? We don't want to use a heavier mobile phone. We want to use lighter mobile phone. We want to push more energy in a small amount of space, right? So that is why actually NMC cells, it is a property of that NMC chemistry that it long last for 300 means 500 cycles, 600 cycle maximum. If you use, suppose in case of mobile phones, if you use LFP chemistry, lithium ferrous or lithium iron phosphate, your mobile phone battery will long last for 8 years, right? Then you will not buy a mobile phone, right? For 8 years. So that is also a loss for a company, right? So 2 to 3 years, 4 years, it is okay, right? So that is why that is a marketing strategy as well, right? So in case of every means whatever the examples actually you have given, mobile phones, electronic gadgets, EVs, home appliances. So most of the cases actually we use NMC chemistry. So that is why actually we are after doing 80% means depth of discharge as well, it will long last for 2 to 3 years. So 2 to 3 years means you are charging your mobile phone on daily basis, right? You are charging your mobile phone on daily basis. Suppose your mobile means NMC chemistry is giving 500 cycles, 500, 600 cycles. So if you do charging everyday basis, so it will long last for 600 days. So yes, 2 years is absolutely correct. 2 to 3 years would be your life after doing 80% SOC as well. If you do 100%, then obviously within 300 means within 1 year your battery will be damaged. Means not damaged, it is actually degrading. So SOC is 100% initially, then it won't be 100% after 1000 cycles. Yes, that state of charge actually, see, guys, SOC is means whatever what your question is, after 1000 cycles as well, your mobile phone should give you 100% data, right? Means whenever you are plug in your charging, it doesn't mean that after 1000 cycle it will stop up to 90%. Means you are plugging your charging for 1 day and you are seeing that your phone is only at 90%. So where is the 10% SOC, state of charge? So it doesn't mean that your state of health is decreasing from 100% to 90% to 80% to 70%. But depending on that present state of health, it will show you a 0 to 100% state of charge. That is the main algorithm behind this, right? I hope you can understand state of charge and state of health, right? Yes, 100% of 90%. Yes, you are right. So that is how actually after 1000 cycles also we are predicting the state of health, not the state of charge. It will be same 0 to 100%, obviously. So okay guys, we actually were, yes, battery pack designing. Okay, so there is thermistor we are connecting. There is a voltage means wiring obviously there. There is a voltage sensors, current sensors we are using. So and there is a communication systems also we are using. There is a wire harness we are using. There is a bus bars we are using to basically connect those means battery pack means positive negative connections. We are using bus bars. Now there is a case study actually I want to give you. Suppose there is a cell specifications actually we are using. From the image itself you can do this. Suppose the cell specifications is 15 ampere hour LFP and the battery pack voltage required is 460.8 volt 150 ampere hour. Then how actually we can connect this? And for your information, every BMS actually can sense up to 24 cells in series. In all over the, means in India especially, I am, because I have seen many BMSs. I have seen minimum 6 to 7 manufacturer BMSs, and I have tested also. So most of the BMS having 24S maximum. Now you have to design a 460.8 volt battery pack. So overall series cell you have to connect is 144. Overall parallel cell that would require obviously 10. So that means the total number of cells you will use, that is 1440. So that is the total number of cells we have to use. Now there is a SBMS that is named as series BMS. So that can series 4 to 24 cells in, means by using a single BMS, you can manage 24 series cells, right? More than that, you have to use another BMS. So we have to use 144 series, right? We have to connect 144 series. We have to control the 144 series as well. So for 24 series, we use one series BMS. Then for again 24, we use one, right? So obviously that would be a one module, that is 24S 10P, means there is a 240 cells, right? So that is one module. In a four-wheeler EV, actually we do actually modular structure. So one module having 24S 10P, right? They are each module holding 240 cells. And this type of modules we are using, six number of modules actually we are using, and which is connected with each other by a CBMS, that is a centralized BMS technique. Means in case of four-wheeler EV, actually you have seen two types of BMS actually we use. One is series type of BMS that can sense up to 24 cells data. But we have to do all the BMS at a time, right? We have to sense all the BMS, we have to control all the BMS at a time. So that is why we used one centralized BMS that is named as CBMS specially. So we are connecting this CBMS. One CBMS can control the minimum 12 SBMS, series BMS, right? So here only we are using 6 modules. So, and roughly the gross capacity we are getting nearly around 69.1 kilowatt hour. So that is how actually you can design your battery pack. That is a modular design basically. So you can see that this is one module of a Kia battery. Means Kia actually use this type of cells, means this type of module, one module, and they have designed with prismatic cells when only. You can see that positive, negative, and that are prismatic cells. You can see there is a bus bar in the upper side, and they are using flexible PCB to sense the voltage. Every BMS actually shared a wiring systems, right? Wiring systems actually they have shared, but mostly the big players, they designed flexible PCB to sense. Obviously, wire having a more drop, right, rather than using a PCB. So that is why Tata also used flexible PCB. Kia, MG, they are big manufacturer use flexible PCBs to sense the voltages properly. There should not be any error in the data. Now there is some market analysis I am showing you. So first one is a Audi Q8 e-tron. The battery gross capacity is 116 kilowatt hour. The configuration they used, that is 108 cells connected in series and 4 parallel, right? So that is how actually we are getting Audi, Kia, Mercedes, Tesla, Rivian, Porsche. So that is the data actually we are using. You can see Audi e-tron GT actually using a very high voltage battery pack, that is 725 volt battery pack. So from this configuration, you can easily observe that there are basically you can see that the upper one, they only use one parallel, two parallel, four parallel. That means they use prismatic cells for that. And if you see that Tesla Model Y, Rivian, Porsche, not Porsche, Rivian, Tesla, they are using 46 parallel, 72 parallel. That means it is a cylindrical type of cells they are using. So that is the configuration basically in the market is going on. Uh, so is there any question, guys, up to now? Okay, there is a question. Mobile phone charges 0 to 100% in only 35 to 40 minutes. In 30 or 20 minutes using 80 watt, 90 watt, 120 watt chargers. Okay. My question is 0 to 90% charge completes faster, and when it comes to 90 to 100% it slows down. It would even take about more than 15 minutes. Why? So that is I have told you, na, all the battery manufacturer recommend fast charging technique from 30% to 80% only. If someone gives you 0% to 90%, that is also not good. From 20% to 80%, it is the safer range for fast charging. Above this range means above 80% or 90%, what you are giving, or below 10%, actually we are controlling the charger current rating. That is the work inside the charger as well as in the mobile phone also. Whatever the charger actually we are using, after that inside the inside the mobile phone itself, there is a current management system we are using. There is also a BMS in mobile phone also we are using a BMS, and also we are using a current control ICs as well. So depending on the SOC, sensing the SOC, calculating the SOC, actually we are controlling the current, right? So if you do same fast charging for 90 to 100%, so it would damage your battery pack, right? It would actually impact your battery health, right? So that is why actually they are giving slow charging during full charge and during deep discharge. Any question, guys? Okay, thank you. So basically we have done the BMS architecture. Okay, I actually, one second, is it possible to show you the data or not? Okay, actually I don't have that image now. Otherwise, I will show you that how actually BMS look like. Means you can search it on Google as well, right? From the Google also you can get easily the means how actually a BMS actually look like. Okay, battery pack component. So this is the battery pack component. Prachiti, I am sharing this. I hope you can see the screen. So these are the components actually. Cells, that is a main component. After that, there is a bus bars, or we can say bus bars is used for connecting the cell to cells, and wires basically are for connecting from cells to BMS, BMS to outer connector. So obviously there is a connector type arrangement we are using in case of two-wheeler, three-wheeler, four-wheeler. In every cases we are using this type of connector. For four-wheeler also we used means active thermal management. I have not shared any thermal management here because that would need a separate session on that thermal management. So that is why I just only give these a three-wheeler battery pack data. So in four-wheeler battery pack, there are active thermal management are also there. There is a housing, there is a communication system, and the sometime in three-wheeler also we use a contactors, that is for overcurrent protection, means that is for hardware based overcurrent protection. If suppose your BMS fails, so that contactor, or we can say MCB, we are using sometime, so it will protect your overall battery pack. So that is the main purpose of use this type of contactor system. Any other question, guys? Okay, then I think I can conclude today's session. So I'm stop sharing my screen. Second, guys.
Yeah, yes, sir.
Yeah.
Yeah,
Yeah,
I'm
Sushmita,
there.
I am concluding the session.
Yeah,
Okay.
sure, sir. You can. Thank you. We'll meet again by tomorrow at 7 p.m. Thank you so much.
Yeah. Thank you. Thank you so much to all of you for participating. Okay, guys. Bye bye. Good night.
Yeah, so dear students, the attendance link has been shared in the chat. A request, if you have not marked your attendance, kindly mark your attendance. As you all know, 60% of attendance is mandatory to get the certificate. Okay, fine. We'll wind up for the day. Good night, everyone. Thank you for joining.